Hi, I'm Natalie. I'm a developer on the Direct3D team, and I am here today to give a high-level overview of D3D12, the API targeting D3D11 developers. So this talk is basically a high-level overview. If you have used D3D11, if you know, I use this ID3D11 interface or these methods to do a particular operation. What does that look like in D3D12? Then this is the talk for you. We are not going to be covered performance analysis techniques for getting comparable perf to D3D11. D3D12 gives you a lot of the responsibilities that D3D11 drivers used to have, and D3D11 drivers are very well optimized, so you can't necessarily expect to reach perf parity with a naive implementation. So this is just a learning experience. This isn't going to be talking about optimization. And we're also not going to be talking about any of the new features in D3D12 which you can use to get alternative implementations. All we're talking about here is direct analogs. I used to do this in D3D11. What does it look like in D3D12? The target audience, the people that should hopefully be watching this video, is someone who is familiar with D3D11 and who is working on a full D3D11 engine. If you dabble in D3D11 or if you make custom tweaks to a AAA engine, then this might not be the talk for you. If you are using a AAA engine, you may actually want to look to see if there is already a D3D12 version of that engine, or if there will be one coming soon. And if so, it may actually make more sense to start with the stock version of that D3D12 engine and reapply any custom tweaks that you have to that, as opposed to porting the entire engine yourself. So let's go ahead and dive right in, starting with resources. So in D3D11, if you were to use any of the ID3D11 resource, or buffer, or texture 1D, 2D, 3D methods, the direct analog for those in the D3D12 world is what we call the committed resource. It gives you an ID3D12 resource interface. ID3D12 device create committed resources, the method you use to create them. You may be asking yourself, what does committed mean? Why would I create a committed resource? D3D12 relies heavily on the WDDM2.0 virtual memory model for GPUs, which is kind of evolving towards the direction of the standard Windows CPU memory model. So a committed resource means that it has both virtual address space as well as physical memory associated with it, which is just like the D3D11 resources that you're used to. So if this is what you used to do, then this is what you want to continue to use. If you had started adopting D3D11 tiled resources, then any resources you created with the MISC tiled flag in D3D11 would be created through the create reserved resource API in D3D12. Again, you might be asking yourself, what does reserved mean? Just like the Win32 APIs for allocating memory, reserved memory is virtual only, no physical memory associated with it, which is basically the meaning of a tiled resource in D3D11. And if you wanted to allocate your tiled pools like you would in D3D11, the API for that in D3D12 is create heap. And this is basically physical only memory, which you can use to map tile by tile or page by page to your virtual memory, to your reserved resources. And then you want to get some data into those resources that you've just created. So in D3D11, the abstractions that we have, it gives the appearance of a single timeline. You do operations and at some point later they happen, but there's no explicit control of whether they're CPU operations or GPU operations, and there's no real indication of how many copies are going on. So the typical techniques that you would use to upload data in D3D11 would be initial data, passing in the D3D11 subresource data structs when you create your resource, or you could use the update subresource method, or you could use the map methods to do it. In D3D12, everything's a little bit more explicit, so now you actually get to choose what timeline your copies happen on. So you have the option of doing GPU timeline copies, where you basically say, I promise that my data is going to be around until the GPU actually gets around to reading it, and then you can get one copy on the GPU timeline. Using the copy texture region or copy buffer region commands, depending on what type of resource you're copying. You can do CPU timeline copies using map, just like you would in D3D11. You map, you get a pointer, you write your data, you're good. We also have a helper method which emulates the D3D11 initial data and updates the resource techniques. This is a 2-copy method. It does a CPU timeline copy of the data that you provide, to make sure that it can live for the appropriate amount of time until the GPU can get around to reading it. And then it'll also issue a GPU copy from that intermediate staging area into the final destination resource. So this is the D30X12 Update Sub-Resources helper. Shaders and state objects. In D3011, you may be familiar with creating a rasterizer state, a blend state object, an input layout, a vertex shader object, all these different kinds of objects, and then you apply them one at a time to the device context. And then eventually when you issue your draw, they come together to actually define what the total set of state is that draw is going to use. In D3012, we have accumulated all of these objects into a single object, which we've termed the pipeline state object. You create it using the create pipeline state methods. There's a graphics and a compute version of that. And you use the command list set pipeline state method to apply it. So it's a single object and a single method, replacing all of these different pieces that you would use to set independently in D3011. Work submission. So in D3011, you don't really have any control over when work actually gets submitted. All you do is you record some rendering commands on your immediate context, and sometime later they actually happen on the GPU. Maybe if you really need to, you can call a flush API or present and things like that will submit work for you, but it's all kind of just hidden behind the scenes. In D3012, just like everything else, it's very explicit. It's up to the app developer to control. So the object that you would use to do this, the primary object that you care about is the ID3012 command list, specifically the ID3012 graphics command list for rendering operations. This is where you would record your commands. It behaves very similar to a D3011 deferred context, if you're familiar with that. Basically, you record your commands, and you get an object that has these commands recorded, and you submit it at a later time for execution. The ID3012 command allocator is the backing store for these commands. This allows you to manage the memory behind the command list at a coarser granularity. It basically exposes the actual memory that the driver is going to use to store those commands. And the ID3012 command queue is a first in, first out queue. The command list that you submit to the queue will get executed in the order that you submit them. And so once the first command list you submit is done on the GPU, then the next one will be submitted for execution. And in D3011, there's no concept of a command queue or anything like that. There's basically a single queue of execution in D3011. Everything is expected to happen serially. When I submit one draw call, then the next draw call is going to happen after that. CPU-GPU synchronization. In D3011, like I said before, there was the appearance of a single timeline. So you submit commands and they happen in that order on the GPU, and that's basically all there is to it. You don't need to worry about keeping memory alive or anything like that. The runtime and driver managed all of that for you. In D3012, it is up to the application developer to manage this CPU-GPU timeline explicitly. So what this means is that if I submit some work to the GPU, I actually need to know what resources and what memory that GPU operation is going to use. And I need to make sure that they are not only still alive, but they actually still have the same contents until the GPU has finished using them. So the way that you do this is you can use an ID3012 fence object. A fence object allows you to synchronize both GPU command queues as well as the CPU. The CPU can signal or wait on fences, and the GPU can signal or wait on fences. So you can use this for bidirectional communication between the CPU and GPU for synchronization purposes. So the rules of CPU-GPU synchronization is that memory must not be destroyed until the GPU has finished reading it or using it. So you basically, if I submit a command list that has some references to some resources, then I would submit a fence signal on the command queue afterwards, and I need to wait until that signal has completed before I can actually go and destroy those resources. Very similarly, memory must not have been overwritten until the GPU has finished reading it. So, as I mentioned before, there's this D30X12 update sub-resources helper, which lets you do a CPU copy and a GPU copy. The destination of that CPU copy and the source of that GPU copy is an intermediate resource. That intermediate resource needs to have the same contents that it had when the GPU work was recorded, all the way until the GPU has finished reading it. So you need to use a fence object in order to wait until the GPU has finished reading your data before you can actually go and overwrite that same memory location with new data. You may be familiar with the D3D11 map write discard flag, which basically allows you to treat a single resource as if it was an endless supply of memory that you could write to. The technique for this is known as renaming, where basically I take the same API object and I rename it so that it actually corresponds to different memory under the covers. And the way that you do this in D3D12 is, again, just like everything else, very explicit. You need to actually allocate additional memory to store all these different renamed buffers. And you need to explicitly reference all of the different locations in your buffers that you want to use. So if I want to submit 5 sets of data upload, that is going to reference a small little buffer. What I actually want to do is I want to take the amount of memory I would normally allocate in D3D11, multiply it times 5, and I would write the first set of data to the first chunk of the buffer, and the second set of data the next chunk, and then so on, until the GPU has actually finished reading all 5 sets of that data. And only at that point am I safe to go and start overwriting again from the beginning. This is the concept of renaming. You need to make sure that the GPU has finished reading your data before you actually go and overwrite from the CPU. It's very important, very easy to get wrong. Debugging tools are going to go a long way to helping you get this right. Resource binding. One of the concepts in D3D11 that is very prevalent is the concept of a resource view. So if you want to bind a render target or a depth stencil or a shader resource, something that you want to read or write from the GPU pipeline, you need to create a view of it. That entire concept in D3D12 has been replaced with the idea of a descriptor. So in D3D11 you have a view object, it's ref counted, it's a full API object. In D3D12 a descriptor is just a small little chunk of memory that sits in a larger API object called a descriptor heap. So in D3D11 you would call the create view methods, create render target view, create shader resource view. Those methods still exist in D3D12. However, the result of it, instead of producing an API object that is, like I said, ref counted that you need to hold on to, all it does is it overwrites a small little block of memory in a larger object, which is the descriptor heap. So step 1 is you create a descriptor heap, and then you can call the create view methods, and you provide locations in that descriptor heap to write your data into, to populate with descriptors. Where you would previously use an ID311 view object in D311 to bind it, what you would now use is a descriptor handle. There's CPU or GPU descriptor handles. For more details, you can go to MSDN or look for other documentation. But the idea is, where previously you would call the device context set methods for set shader resources or set render targets. Now, it looks very similar. You want to use the ID312 command list set descriptor tables. You pass in a pointer to a range of descriptors in your heap, and they will be bound as a single table. I'm back. I had to get a quick drink of water. But now let's dive into a little bit more detail about the resource binding model for D3D12. So in D3D11, there's a one-to-one mapping from an API bind slot. For example, if I call VS set shader resources for slot 1, I'm binding an SRV directly into the vertex shader register T1. It's pretty straightforward. It's a one-to-one mapping all the way from the API to the HLSL. In D3D12, in order to add more flexibility, we've kind of broken that implicit one-to-one mapping with a more explicit, more expressive model. So what this means is that we have this object which is called a root signature. And the root signature describes a mapping from an API slot number. So for example, I can say root parameter 1 corresponds to a descriptor table, and this descriptor table can contain things that will map to VS T0 through T3, and then it can also map to things like PS constant buffer 0 through 2. It's very expressive, and it allows a complete disconnect between the HLSL register space and the API bind space. the one requirement that we have is that the app is responsible for renaming descriptor tables. And what this means is that when I want to bind a descriptor table at the API, I no longer get to say that I'm going to bind T1 with this descriptor, and then I'm going to bind T2 with this other descriptor. Descriptors are bound in tables. They need to be contiguous in a descriptor heap. It's like passing in an array. The hardware is actually going to index straight from one descriptor into the next using the descriptor heap. So all descriptors need to be contiguous, and you bind them by passing in a pointer to the first descriptor, and then the hardware will index the rest of them. So if I say that I'm going to declare a descriptor table and it's going to have 5 SRVs starting at T0, I pass in a pointer to a descriptor that corresponds to T0, and I need to make sure that the rest of the descriptors there correspond to the descriptors that I want bound to T1, T2, T3, T4. It's kind of complicated. It's a little bit hard to wrap your mind around at first. So play around with it, look up some more documentation. This is just a high-level overview. But that's the general idea. Is we've added more flexibility to the binding model to give a disconnect between the API bind space and the actual shader registers. So, like I mentioned, the app is responsible for renaming of descriptor tables, where previously the driver would have been responsible for that before. So you could actually bind a single view to T1 and then draw and then bind a different view to T1. In that particular scenario, the driver probably would have copied all 128 descriptors that you referenced in that first draw into the second one and then overwritten that one that you wanted to overwrite. Now it's all up to the application. It's all very visible to the application. So you can actually get an idea of what the performance cost is of changing a single descriptor per draw. And you actually get to control it by controlling how many descriptors are in each table that needs to be renamed on a given draw call. Additionally, you can actually control which descriptors are shared between shader stages, which is a new feature for D3.12. So in D3.11, UAVs were shared between all shader stages in the graphics pipe. So if you had a UAV declared at slot 0, it was slot 0 in every shader in the pipeline. Now you can do that with any descriptor type. You can do it for constant buffers, you can do it for UAVs. You can also actually break apart the UAVs, and you can declare specific UAVs targeting vertex shaders or pixel shaders. So again, full flexibility for full orthogonality across the entire pipeline. As an example of what a D3.11 root signature might look like, basically root parameter 0, again just an API virtual construct of a binding slot, could correspond to a descriptor table which contains the vertex shader descriptors of constant buffer 0 all the way through constant buffer 13. Root parameter 1 would be a descriptor table that's vertex shader descriptors T0 through T127, etc., all the way to parameter 14 as the domain shader samplers, for example. And then root parameter 15 would be, like I mentioned before, the shared across all shader stages UAVs. So D3.11 on 12, which is a component that allows you to use the D3.11 API to drive the D3.12 API for interop scenarios. This is what its root signature actually looks like. The next topic that I want to talk about is resource state. This is a completely new topic for D3.12. The D3.11 side is blank. This is all driver managed, it was all automatic under the covers, but this is something that we are now exposing to the applications. This is a requirement in order to get full parallelism of recording command lists. This is one of the reasons that deferred contexts were very hard to implement in D3.11, was because there was no guarantee of the recording order versus the execution order, so tracking the state from one deferred context to the next of these resources became very tricky. But now that it's fully explicit in the API, the app is responsible for informing the driver of all these state transitions. So the app is responsible for understanding the recording timelines, which may even be parallel, versus the execution timelines, which are eventually going to be sequential. So a resource state transition corresponds to a few different operations. This can be something like a fine-grained synchronization. For example, if I was using a resource as a render target and then I want to use it in the vertex shader as input on the next draw call, because there's a graphics pipeline, there can be multiple draw calls in flight at various stages of the pipeline. and you may need to insert what's called a bubble in order to put a small stall so that the data written by into that render target in one draw call would be accessible to the vertex shader of the next. Otherwise, the vertex shader might have already passed by the time the render target was actually full of data. So synchronization is one reason for resource barriers. Another is cache flushes. You need to flush output caches and invalidate input caches to make sure you're getting the most correct data into your resources. And there's also going to be some memory layout changes as well, such as render target or depth stencil compression. Additionally, this all corresponds to the D3D12 resource transition barrier, so this is state transitions. There's other kinds of barriers.
I believe that we have a video that Seb did.
Oh, great.
On state and resource barriers.
Correct. There is a video
Yeah.
available on suggested implementation techniques for how to track resource state in an engine that's designed around D3D11. So you can find additional information on that by looking at another video.
Hot diggity.
So other barriers, there's multiple other kinds of barriers in D312. One of them corresponds very closely to something that existed in D311. This is the tiled resource barrier, introduced to allow using the same physical memory between two different tiled resources. This still exists in D312. We've called it the aliasing barrier. Not only does it correspond to tiled resources, it also corresponds to using placed resources, which is another feature that I'm not going to go into depth right now, but you can use the same physical memory for different kinds of resources. And additionally, we have the UAV barrier. So in D3D11, any dispatch operations that went back-to-back or draw operations that went back-to-back that reference the UAV were required by the API definition to be serialized. Even though, like I mentioned before, draws can be pipelined and UAVs can actually happen, or dispatches can actually happen in parallel. So for D3D12, we have added an explicit UAV barrier. So by default, if you issue two dispatches back-to-back on the same command list, there's actually no guarantee that they're going to happen sequentially, unless you issue a UAV barrier between them. And that allows you to ensure that any UAV operations that were done by the first one will be available for the next one. So there can actually be significant perf gains to be exploited by knowing the correct times to insert these UAV barriers. When your operations can actually run in parallel, you want to let them run in parallel. You can get significant perf gains. There's actually a talk, I believe Max, the development lead for D3D, mentioned at the build conference that this was an example of some significant perf gains that were gained during the Fable development cycle by allowing UAVs to, dispatches to run in parallel. Swapchains. You still use DXGI swapchains for D3D12, just like D3D11. There's some minor differences that you need to be aware of. D3D11, the swap effects that are available, you have the sequential discard, flip sequential swap effects. D3D12, you've got flip sequential and a new for Windows 10 flip discard swap effect. There's another talk that will go into more details about these and what the performance implications are and how to actually use them. So that's a high-level overview of what's available. The other detail that you need to be aware of is that D3D11 provided automatic buffer rotation. What this meant is that you could call into your swap chain and you got back buffer 0, you create a render target on back buffer 0, and you always write to back buffer 0, and that's it. That required a bunch of work under the covers in order to make those render target views actually point to different memory locations on each present. And again, this is one of those things that can kill parallelism and increase overhead significantly. So for D3D12, it is all explicit up to the application. We've removed the implicit rotation. It is now the app's responsibility to render to the correct back buffer on each frame. We've provided a helper method, which is the get current back buffer index method on the new Swapchain interface for Windows 10, which allows you to see what back buffer should I render to for this given frame. There was a bunch of fixed function rendering functionality available in the D3D11 API. Even though most of it was programmable shader pipeline stuff, you still had some functions like generate MIPS or draw auto, which were able to generate full MIP chains or take the output from stream output and use it as input to a vertex shader without any additional manipulation from the app. Both of these have been deprecated in D3D12. The app is responsible for creating shaders to do these operations. And at some point in the future, we may provide helper examples in the D30X12 library to aid applications in replacing these methods. And lastly, I want to talk about a bunch of other things that have changed somewhat slightly between D3011 and D3012. You may or may not have used these. These are maybe some edge cases or things that didn't change very much. So queries and predicates in D3011. There is now an ID3012 query heap object, which allows you to accumulate queries together and amortize the cost of doing queries. ID3011 predicate no longer exists. Predication is just done by using data located in a fully transparent buffer. The app can actually write this data using the CPU or the GPU or any technique, and you can do predication very simply. The getData method on the D3011 queries and predicates is resolved by getQueryData, followed by a GPU sync operation. You'll need to issue a fence to wait until that data is available, and then you can map your buffer and read the data. The UAV and streamout hidden counters that existed in D3011. You may remember that when you called set UAVs or SO set buffers, that you could pass in an array of these counter values. -1 that don't do anything. It's kind of special sentinel value. These are now exposed out of the API in D3012. The app is responsible for allocating and managing the values of these hidden counters. D3011 had a resource dynamic min-LOD functionality. There's a set resource min-LOD. This no longer exists. It has been moved to the D3012 SRV descriptors. Draw indirect and dispatch indirect have been merged together along with a bunch of additional functionality into the execute indirect method. I'm sure there will be another talk about that, or at least you can look at documentation. The depth stencil formats have changed somewhat significantly between D3011 and D3012. So if I had a D24 S8 format in D3011, that meant that I had 24 bits of depth data and then 8 bits of stencil and then 24 bits of depth and 8 bits of stencil. In D3012, what we've actually done is we've separated these out into a planar resource. They look a lot more like the video formats, the YUV planar formats. What this means is that you actually have 24 bits of depth, and then another 24 bits of depth, and then another 24 bits of depth, and then somewhere else you have 8 bits of stencil, and then another 8 bits of stencil. You can look at the documentation to get more details about this. Another deprecation between D3011 and 12 is the resize tile pool method. If you use tiled resources and you figured out that you needed more tiles to populate your resources, you could use the resize tile pool method to get more tiles. In D3012, again, this required a lot of tracking on the driver side, so it's not really possible in D3012. Instead, we've added the ability to map a single tiled reserved resource into multiple different heaps in D3012. So you can actually do this resize operation yourself by creating an additional heap for those additional tiles that you need. And I think that about wraps up everything that I had in mind. My name is Natalie, and I will see you next time.